Let's talk about rotational energies and energies in general. So far, what we have learned is that if you have an object going from one point to another point with some sort of velocity. So here, for example, I have an object, looks like a box. Mass of the object is m, going from point A to point B, traveling a distance d here. And it goes with some sort of velocity v. We can assign kinetic energy to this moving box or to this moving object. That kinetic energy was half mass times velocity squared. Okay? And I wanted to label this because this is translational kinetic energy. The object is moving from one point, point A in this case, to another point, point B. Okay, so I'm going to label this T to indicate that this is the kinetic energy associated with this motion because an object is moving from one location to another location with some sort of velocity. Okay, we have another type of kinetic energy, and that's called rotational kinetic energy. Rotational kinetic energy, for example, if you have a disk that's rotating, it doesn't move from one point to another point. It just rotates around an axis. Okay, so an axis point here, and the object is moving around that axis, like a CD or a DVD that rotates around, or a disk. All right, we have a top view at this point, but if we can also have a edge-on view. Okay, if we can have an edge-on view, it would look like something like this. The object can rotate either clockwise or counterclockwise. All right. So, and that's that axis of rotation. In this case, the object is moving. It has a velocity, but it does not move from one location to another location. It simply rotates. And because of that rotation, we assign some sort of energy to this rotating object. We call it the rotational kinetic energy, and we're using this formula. Kr indicates rotational equals half I omega squared. It is very close to what we have here. So we have half mv squared, we have half I omega squared, okay? Over here we have half mv squared, we have half I omega squared. So these are looking very similar, but for rotation, I is moment of inertia. This I is related to the mass of the object and the radius of this object. For example, for this disk, this would be the radius r. Okay? So not only depends on the mass of the object, but also depends on the distribution of the molecules. All right? So for example, if you have a piece of metal, a rod or something, all of these molecules in that metal are distributed in a different manner compared to if you have, let's say, a cylinder. Okay? The distribution is different because this radius r is a lot bigger than this radius. Okay, so moment of inertia, I here depends on the distribution of the materials, the r, and also the mass of the object. And you don't have to memorize it. It's usually given. It's usually half mr squared, 2/5 mr squared, something like that. It's usually given to us. It depends on the shape. Okay? Omega, on the other hand, is very close in terms of the definition to regular velocity or linear velocity that we learned so far. So omega is delta theta divided by delta t. Theta is the angle. So let's say that you have an object located here, this point, okay, and it's moving counterclockwise, and it goes to here, 0.1, and then it goes to here, 0.2, and so on and so forth. So 0.1 has theta 1, 0.2 has theta 2, and delta theta is theta 2 minus theta 1. Okay, this is called angular displacement. So this is angular displacement. This is the omega, or angular velocity. So again, angular velocity, angular displacement divided by time. What was the linear velocity? Linear velocity definition that we learned. V is delta x divided by delta t, or delta y divided by delta t. Again, displacement along the x direction or y direction divided by delta t, the time. This will give you a linear velocity. Here we have omega, angular velocity. We have angular displacement, delta theta, going from 1 to 2, divided by delta t. So back to our rotational kinetic energy is half I omega squared, half times moment of inertia times omega angular velocity squared. Now, what's very important to know is that an object can have both. For example, we could have a rotating cylinder. So not only this cylinder moves from point A to point B, okay, with some sort of velocity v, but when it's doing it, it rotates with velocity, angular velocity omega. So K total kinetic energy is translational kinetic energy plus rotational kinetic energy. In other words, it's half m v squared plus half I omega squared. Okay, so here, again, m is the mass of the object, I is moment of inertia, v is linear velocity, omega is angular velocity. Because not only the object moves from point A to point B, but it rotates as it moves. So it rotates going from point A to point B. The last formula that I want you to remember before we dive into deeper to the definitions and other stuff is that omega is related to velocity, okay? Velocity, linear velocity is r omega, okay? Linear velocity is r omega. In other words, this linear velocity is the radius times omega. Or in a lot of textbooks, we have seen that omega is v divided by r. Linear velocity divided by r will give you omega. So they are related, okay? So I can rewrite this equation one more time, K total, to be half m v squared plus half I. Instead of omega, I'm going to use v over r, v divided by r squared. And this I will be given to you. Usually it's given to us. All right, let's take a look at the things that we're going to do in the lab. So the first part of the experiment is this, that we have a air track, all right? And so I'm going to show an air track here. An air track is a hollow air track. There are a bunch of holes, and this is connected to a blower. And so the blower is blowing air out of these holes. And the purpose for that is to just have less friction. Then we have a glider, all right? So I'm going to show a glider here. Glider is something that can easily glide. It has two sides. One side is the other side of a air track that you can't see from here. But then the other thing that we have is that we have a flag on top of this glider. And we will provide you with the width of a flag. Okay, the purpose for the width of a flag is that whenever that we have a photo gate and the glider is passing through the photo gate. The photo gate, using the width of a flag, which is also given, will give us the velocity. Okay, so very simple. What I have is a very easy setup. All right, I have a wooden block. I placed it under the air track. All right, it's a wooden block with height h. All right, that is given to us. I left one side of the air track. Now the glider is exactly above the wooden block. All right, so this is wooden block. All right, and that's the flag right here. All right, we'll start the air blower. The air is blowing out of those holes right there, and what's happening is that they will reduce the amount of friction. We'll let the glider to go from point 1, exactly where the block is, the wooden block is, from point 1 to point 2. Going from point 1 to point 2, which is where the photo gate is. Photo gate does a very interesting thing. Photo gate has a laser beam. As soon as it's blocked by the flag, it'll start the time, okay? And when it's unblocked, it'll stop the time. So you have the time that the flag was between the photo gate. In fact, it was blocking the photo gate. All right, so then you can measure the velocity. Again, velocity is delta x divided by delta t. This is the flag length, or the width of a flag. T is time that the photo gate is giving you, so you can find the velocity of a glider when it passed through the photo gate. Okay? Now, the purpose is to see what energy is transforming to another energy. In point 1, we only have potential energy, m, mass of a glider and a flag, times g, times h, height. This is height of a wooden block. Okay? In point 2, we only have kinetic energy. Translational kinetic, nothing is rotating. Translational kinetic energy, half mass of a glider and a flag, velocity squared. Where do I get the velocity from? I get velocity from here. Okay, so this velocity is delta x divided by delta t, width of a flag, which is given to you in the data, divided by time, which is given to you. So you see how much of the initial energy is being transformed to final energy. Is there anything that's missing? Is there anything that's wasted? Is there anything that friction took? So this is 100% of energy, initial energy that you start with, mgh, right? Gravitational potential energy, all right? But here is kinetic energy, final kinetic energy. Okay, so point 1, we have initial 100%. Point 2, we have final. It should be less because a little bit of the energy is wasted through friction. And second part of the experiment, we will do the same thing, but this time we'll have an inclined surface. So what we have is a wooden block. Okay, this is a wooden block. One side of that wooden block is tilted with a block with height h. Okay. We have a photo gate here at the end. But this time, instead of a glider that can glide, we will use a solid cylinder. All right, we'll use a solid cylinder to be able to release it from point 1, which is exactly above the wooden block, to point 2, which is where the photo gate is. So we're gonna let this to roll down. This is a solid cylinder, okay? Not only it's rolling down, but it's rotating and rolling down. So it has omega, which is rotational kinetic energy. So point 1 has U, which is mgh, mass times g times height of a wooden block. They're all given to you to the data. In point 2, we have kinetic, but not only we have kinetic R rotational, we also have kinetic T translational. So in other words, we have half I omega squared. Okay, so all right, not only we have that, but also we have, oopsie, we do have plus half mv squared, okay? And that v is linear velocity. So kr is half I omega squared, kt is half mv squared, but when it goes to point 2 through the photo gate, we have both. We have rotational and translational, okay? And then your job is to figure out how much of the energy is lost. If you start from 100%, how much of it is lost? How much is rotational kinetic energy? How much is translational kinetic energy? All right, how do we find omega? Omega is V divided by R. For solid cylinder, I is half I is half mr squared. Okay, so let's use these two and find total energy at point 2. Kr plus kt equals half I is half mr squared omega is V divided by R squared. All right, so that's half I omega squared plus half mv squared. So let's take a look to see what we have. We can cancel stuff out. This r squared, this r squared can cancel out. Half times half is 1 over 4. mv squared is left, plus half mv squared. Okay, so what I have is 3/4 mv squared for solid cylinder. For hollow cylinder, we do this. This is the third part of the experiment. We do the same thing for the hollow cylinder. So point 1 starting, point 1, we have U, which is mgh. For point 2, we do have kinetic rotational, kinetic translational. Half I omega squared plus half mv squared. I for hollow cylinder is mr squared. It's not half mr squared like solid. It's only mr squared. So if you use that, well, let's see what we're going to get. Point 2 will have half I mr squared. Omega, okay, is V divided by R squared. So all I'm doing is this omega is V over R plus half mv squared. What I'm going to do, I'm going to cancel R squared with R squared. Okay, so I'll have half mv squared plus half mv squared. Half mv squared plus half mv squared. Half an apple plus half an apple. You'll have 1 full apple. So I'll have 1 full mv squared. So in point 2 for a hollow cylinder, your total kinetic energy is mv squared. For point 2, for a solid cylinder, it will be 3/4 mv squared. Your job is to see how much of the initial energy is lost. You start with 100%, how much you get at the end. For a hollow cylinder, the same thing. You start with 100%, how much is left, okay? Which in this case is only mv squared. So all of this stuff will be provided to you. You can do your calculations. And for the cylinders, when they pass through the photo gate, again, the photo gate should give you the time, okay? And the width or the diameter for these cylinders will be given to you. And the velocity that you have here is that diameter that's been given to you, which in this case is delta x, for example. We call it delta x, but that's diameter, the displacement, divided by time that the photo gate is giving you. The first part of the experiment, we're doing it for glider with a flag on. The initial height is given to us because we have a wooden block, so the initial energy is gravitational potential energy in point 1. As we are letting the glider to glide down from 0, it passes through the photo gate, and photo gate will provide us with the velocity in point B. The second part of the experiment, we'll do the same thing, but this time we're doing it for a solid cylinder, going from point 1 to point 2 where the photo gate is. But this time we have both rotational and translational kinetic energy. The third part of the experiment, we'll perform the same experiment, but this time we'll do it for a hollow cylinder.